Good evening, all. I'm Mrs. Savita Ramesh, Assistant Professor from KMIT. I welcome you all to today's session. In our journey of this FDP, this is the third day. On day one, we had the general topics on IoT in healthcare and the protocol stack. Yesterday, moving on to the core, you all have understood about sensors and actuators and intelligent day-to-day communication, as well as we throw some light on applications of IoT and medical devices. And of course, the much appreciated part yesterday was the hands-on sessions. We will see if it is possible to extend the same today also. Coming to today's session, we have a very good combination, an academician and an industrialist, one end to the other, Deshi Pardesi. Sir is a principal from Osmania Engineering College, Osmania University. And we have another speaker all the way from US going to take up the sessions. Well, today's topics are IoT based healthcare by Dr. P. Chandrasekhar, and we have data management and big data analytics in IoT by Mr. Naidu. Anyway, before we start the session, let me introduce our eminent speaker to the audience. Today's speaker, the first speaker especially, is a renowned academician, Professor P. Chandrasekhar Garu, an MTech from JNTU Hyderabad, and he has 3 doctoral degrees from Osmania University. He had been awarded with postdoctoral fellowship by Shizuoka University, Japan, for 1 year. His journey as a faculty in EC department to the current position as the principal of University College of Engineering, Osmania University, has been very fruitful. During his period, he has contributed tremendously in various capacities like head of the department, vice principal, director of evaluation, chairman BOS, etc., etc. He is actively involved in establishing the state-of-art laboratories in the department. Prior to teaching, he also has 8 years of industrial experience of design and development of embedded system. Coming to his research contributions, he has more than 50 research publications and a patent titled Improvement Real-Time GPS RF Data Capturing for GNSS SDR applications to his credit. He delivered more than 20 invited talks and guest lectures in various conferences and events. 16 doctoral students under his guidance have completed PhD. He has executed UGC-sanctioned major research project or GNSS receiver baseband algorithms in FPGA worth rupees 15 lakh. He successfully executed 2 consultancy projects from DLRL and RCI. Currently, 2 research projects are being executed. A project titled IP Core Development of Novel ADPLL of worth 5 crores is sanctioned by METI under Chip to Start C2S program. Another project titled Development of GNSS Waveform Generators and Receiver Algorithms for use in SATCOM Toolbox worth 20 lakhs is also sanctioned by MathWorks Private Limited. Professor Chandrasekhar has received Best Teacher Award from several government and non-government organizations for his outstanding skills in teaching and research. His expertise and services have been utilized by several institutions in various capacities like Board of Studies, Governing Body Member, Peer Review Committee Member, etc., etc. His research interests include development of high-performance computational, electromagnetic, and efficient FPGA-based signal processing algorithms, hardware accelerators for machine learning, and design automation. We really look forward to hear from you, sir. I welcome you to the session. Audience, please take the best out of this. Thank you,
Thank
sir.
you.
Welcome once again.
Yeah, thank you, madam. Thank you for introducing me. And my dear participants, a warm welcome to all to this ATAL workshop faculty development program. Yeah, mainly um, healthcare, agriculture, there are the different sectors where technology driven solutions have to be given. Still, there is a scope as mainly our India is a rural dominant sector. Healthcare as well as the agriculture are the two different sectors where, so hope you are able to see the screen. So
Yes, sir.
we are- yeah, we are working in these two different domains in the university, as we have one of the important departments called Department of Biomedical Engineering we have, and as well as agriculture also is of our interest. The two different sectors we are working at the sensor level development and all we are working. So keeping that in view, so started giving some idea, right, what is going to happen in future. So where IoT is one domain and artificial intelligence is another domain. So if there will be a framework in future where these two will be integrated, artificial intelligence and IoT, both have their own advantages. Once we start working together, definitely the advantage of both the technologies will be taken into consideration for developing healthcare products. So they are the two different transforming techniques to give smarter diagnostics. So mainly, so we should give the ease of treatment to the patient who is already suffering. So whatever the technologies are there, they have to give ease of treatment or diagnostics to him or her. So this AI will enhance the decision making. So what is the treatment we have to give? How depth we have to give the surgery, or what is the protocol we have to use for all those things? Standalone human being instead of taking decision, this artificial intelligence driven decision maker definitely gives a better solution to the patient. Whereas IoT is mainly concerned about the real-time monitoring, because, as I mentioned, healthcare or agriculture are two sectors where continuous monitoring and real-time monitoring is very important. Especially in healthcare, whatever the decisions we take, they are all real-time based decisions. So this is the decision we have to take now. Now, for example, now time is 6:15. We have to take the decision 6:15, not tomorrow we have to take the decision. So these real-time decisions are real-time system which is adaptable to the IoT, whereas AI will give the decision maker, and efficient decision making will give. So together, when we use artificial intelligence and IoT, a real-time solution with enhanced decision making. So this is the market, what we are predicting. AI already you know very well. Even today also we had a summit, right, at at the international level, where the next year we are going to have a summit at the international level in the India in our country. So it is going to be a boom in artificial intelligence. There is no doubt about it. Whereas IoT also is picking up, where IoT also needs to be embedded into the market. So we know very well. So already we have some of things are existing, like variable and remote monitoring. So where so we wear something like a watch. See, here is a watch we have. So this is going to give monitors. It's something like a watch where we can embed biosensors and, for example, continuous glucose monitoring to track vital health data in real time. So that is the basic advantage of IoT based. So these technologies will help us to give early detection. So this is another important thing. Early detection, any disease, whether it is cancer or any other lung problems or any problem, if we take, if we can give early detection, definitely treatment will be in a better way and patient will be cured to the maximum extent. So that's the reason why, so early detection or early detection of the diseases is going to be a prime concern now in the healthcare system, healthcare monitoring, where AI or IoT or any technology-driven solutions are focusing on that. And remote patient monitoring. So as we said, so always the doctor cannot reach, a patient 24 hours. Even then, doctor can monitor the patient health history, and quick decisions can be taken so that patient will be cured in a better way. So, and then these are the smart hospitals. So, what we can expect is smart hospitals, where hospitals are automation. It improves the efficiency, and smart sensors, so that resources are optimally allocated or used. So, this is again another important thing. So, sensors have to be used optimally. So, these are all the concern about the IoT based systems. And this is there are different companies already coming. IBM, Path AI, and Cori AI are leading AI driven medical diagnostics. So they give the diagnosis to assist the medical doctor. So these AI assist detecting cancer, heart strokes, and rare diseases faster than human doctor. So human doctor may sometimes fail to give the solution, or may fail to give the diagnosis, whereas AI will give a better solution or better assistance to the doctor. We can't replace the human doctor. However, this AI system will assist in a better way to the doctor. So then already these are the technologies coming into the picture. Robotic surgeries. So instead of manual surgery, so robotics are coming into picture for the surgery to some extent already for heart problems, and even other problems also. Robotics are being used at the different extents. We are using it. So mental health AI, so it is going to give the mental health care also. It is going to give real time diagnostics, will give faster results, diagnostic results to this. These are the breakthroughs in AI along with medicine. So what is that next is AI. As I mentioned, AI is different and IoT are different. But when both together, when we have this one, so what is the advantage? There is synergy. One is enhanced IoT. It is giving the health outcome. It predicts health outcome in an efficient way, and a smart wearable. So it is a wearable device where data collection and analysis can be carried out in a better way. And proactive healthcare, as we mentioned, so early detection can be done so that quick decisions can be suggested by the medical doctor. So these are the advantages are going to be there with AI connected, joined with IoT system. So, and when we use AI, we are assured of giving the performance. What do you mean by performance enhancement? One is the precision. So when a human being is performing the surgery, sometimes they may cut unwanted thing also. Whereas precisionly, exactly how much part we have to cut it, or how much part we have to give the surgery. So these decisions can be taken at the AI level in effective way compared to the human being. And obviously there are it minimizes the human error. As a human being, our focus may not be there, our attention may not be there 100%. But as a AI, because there is no human being brains there, so it minimizes the errors. And obviously patient will be recovered in a better way compared to this one. So obviously they overcome in a better way. So what are the different case studies available in the market? So one is AI in oncology. So IBM Watson, they're already working on this. So IBM Watson analyzes millions of medical records. This is again, so we know very well where the huge data. That's what the next lecture also is on the data science. You have the next speaker is going to speak. So artificial intelligence we use where the bulky data is there, bulky data to be analyzed, where human being next to impossible to know that particular thing. So AI, this IBM Watson person is analyzing millions of medical records to recommend cancer treatments. So a doctor may have an experience with an experience. They will be working maybe 100 records, 100 patients he or may she may be studying, whereas millions of medical records when AI studies, and it gives a better recommendation for the treatment. So medical record analysis, and then obviously once we are accurately or precision level we are working, it reduces the error and faster insights. So it is going to look into the problem in a better way, in the in-depth it gives, and obviously performance, that is precision, is enhanced. So precision enhanced, and reduction in error and faster insights. They are the medical records also will be in depth. They will be studied, analyzed by the AI based system or based solution. This is DeepMind is another solution by AI for eye diseases. So eye disease detection. So it is detects over 50 eye diseases from retinal scans with a high accuracy. So 50 types of diseases can be detected using this particular AI solution. Obviously, it gives early detection, and it reduces the permanent blindness, so risk worldwide. So for example, there are some problems. If we go little late, so these problems may not be solved. So that they may lose the vision permanently, and the patient may be suffering. They may have to suffer lifelong with blindness or with bad vision. So such problems can be addressed when we go with the early detection, as well as high accuracy when it is done. So this is one direction towards that. And then genomics is another thing we have. So it is going to study the genomic data for precision oncology. So how the genes, how the is working. So nowadays DNA study also is connected with AI, so that they give better solutions. Even people who are working in DNA analysis identify best treatment based on the patient DNA. So this is AI for radiology. This also is another. To some extent, we started working on this particular thing at the manual level, right? By taking digital images, we have given some solutions here. Already, one of my PhD scholars worked on this particular thing. They take the CT scans, and they give the solution for this. Then the next level is machine learning. That's what artificial intelligence for the radiology. So this is going to scan X-rays, MRIs, CTs for early disease detection. Because CT scan also, there are several images we have. So human being sometimes they miss a particular minute things also. Whereas this AI will scan in a proper way and in a better way, in the in-depth they will scan and give the solution. AI helps radiologists work faster with greater accuracy. Another important point for the radiology is how what is the space it has to be exposed, what is the subject it has to be exposed to the radiology, because you know very well radiology will kill the cells. So therefore, what exactly, how much space, how much subject, we call subject, it has to be exposed. This also is estimated accurately, precisionally, when we use artificial intelligence, so that the better, good tissues or good cells will not be killed. So which is very important for the recovery to the patient when they are exposed for the radiology. So these are all the things what exactly what we have just scanned in the present things. So what is the next trend is predictive analysis. So this is again very very important thing called predictive analysis. Analytics will take the existing medical records and keep them as the knowledge, and they will give predictive analysis. Analytics will do it depending on the database. They are going to do that, so that patient analysis for the patient data, it can be done. It forecasts the diseases outbreaks as well as the pandemics. And second part, very important thing is AI assisted surgeries is also, as we mentioned, robotic surgeries already in place. So they will be in a better way, they will be used. And then third one is digital twins. So these are the future trends we are what we are thinking. So AI chatbot will for mental health support it is going to give. It provides mental health support anytime, adapts to individual needs. It is all personalized. So one person problem may not be with other person problem, whereas this is going to assist a particular person's problems in a better way. So this is going to be there in future. So, as we mentioned, so our robotic surgeries, AI-assisted surgeries also will be in picture. So there will be in depth in the larger way, in the larger extent, they will be used in the hospitals. And role of generative AI. Yeah, this is another domain. So we know very well generative AI is going to play a very important role. So now, I mean, enhanced AI, that's what is going to be used. So this also in the healthcare, it is going to be used. One is medical images. When we AI generated medical images, we can get it, and synthetic data that is based on the existing data, that is CT scans and all. It is going to enhance the decision support. This is what we can. And then training and research. So patients need not be physically available to them. Virtually they can talk to them and give the treatment diagnostics as well as the treatment. So, and another thing is, yes, this is again mainly towards computer science and electronics simulations. So we will be most of the times engineers will be working on the simulations. So whereas doctors will be directly working on the patients. Sometimes it may be difficult to work with the patients with all types of medical problems or health issues. Whereas this simulated training will provide them to understand different modelings, will give them to understand how to face different problems. So it gives simulations, realistic training simulations, because all the scenarios, they may not come into picture at the time of training. In practice they may get all type of problems, but at the time of training they may not get all kinds of issues, all kinds of health problems to them. Whereas all the scenarios can be created or simulated in the virtual environment. So virtual patients is another domain. So medical doctors, when they are taking training, they can work on that. So detailed patient replicas. So this is also is another thing where we can work and train doctors without patient risk. So because they don't need to experiment on the patient directly, instead they'll be working on the simulation virtual patients, so that the real patients will not have any problems or mistakes of the doctors will not be there on that. So this is again another thing which is very important, which so far only engineers have this advantage of having simulations. So whereas now this is extended to the doctors, so that they will understand in a better way. So, what is going to be future AI connected with IoT? So, it is going to redefine the medicine. So now, earlier the diagnosis, earlier protocols, earlier methodology is going to be entirely different. Now, it is going to be there. That is redefining medicine, transform healthcare practices, and then it is going to improve the efficiency, because it is going to streamline the medical processes. So it is going to standardize the medical practice processes also, so that because we know very well, so one doctor opinion may not be with other doctor opinion. So like that, we also face some problems. But when machine is working, when machine is giving the decision maker, so obviously it doesn't depend on the human errors. So this will give streamline the medical processes also. And then yeah, increase accessibility. This is very important, which is at the Indian scenario very important. Accessibility is it is a right of every human being. Every citizen of our country is to be access to the healthcare. It is not that only reach of urban people or rich people. So this healthcare has to be it has to reach everyone. It has to be accessible to the all the citizens of our country. So this is going to happen when virtually a doctor from one place to treat a person who is there at the remote. So these are the things can happen when we have AI connected with IoT is possible. So these are the different things I would like to discuss at this point with you. And another point I wanted to tell is IoT also will be going for the standardization. Standardization is very important in IoT because IoT also has to be standardized. Standardization of IoT is very important. Otherwise, whatever the IoT system X develops, so it has to be work with Y system also. So that is again very one serious problem usually we face when we are using IoT based systems. This standardization will help us so that um, across the country, so all these systems can work, can talk each other, so that it gives a better solution. So IoT standardization is another important domain where we I mean some researchers are working in this domain, working on this particular thing. And then decision making will be done based on the data collected from the IoT systems, and then using deep neural network or machine deep learning techniques we are going to use. So this is going to be there, and then these are all the things will assist the medical doctor to take an appropriate decision to a patient, so that patient will be having less pain when he or she will be in the treatment, when the treatment is going on. However, some of you might have seen today. So Padma Vibhushan, Nageswara Garu, so he was talking in today. So no artificial intelligence will supplement doctor, obviously. So they're all only assisting systems to take an appropriate decision to the medical doctor. We can't, no AI system will supplement or replace medical doctor, right? However, these are all the things will help the doctor to take an appropriate decision. So these are the things I would like to mention. So if you have anything, you can ask me.
Questions are welcome. Audience, anything you want to clarify from Professor Chandrasekhar Garu, you are most welcome.
In fact,
Yes.
we are also working in another important domain of machine learning or deep learning. So this is actually, I am actually, in fact, I am from electronics background. So we were as I was introduced that I worked in postdoctoral fellowship in Shizuoka University, Japan. So where we were working on high performance computing. So this is again another domain where computer science and electronics researchers can work together. High performance computing. So we were working on CUDA processors, and OpenCL is another programming language. So that time, not today, I was telling about 20 years back or 15 years back, we were working on that. But suddenly, so what we have realized just 1 year back, that machine learning or deep learning can be used for CUDA processors. That's what already you may be using. So we are going. Another important domain. People can work is accelerators. So accelerators where we can use these particular CUDA processors, that is called GPGPUs. So GPGPU CUDA programming you can use for the accelerators. Accelerators we can work. Yeah, one of them, Sandeep Challa, is asking that any real-time problem statements as one second, as real-time problem statements, as I am working on fracture detection using RCNN. Yeah, so okay, fracture detection, RCNN is one technique. So you definitely we now there are several advanced studies are possible for the detection of the fractures, right? In addition to RCNN, in addition to RCNN. So that's what I was telling about it. These machine learning algorithms, whatever you are working on high performance computing, we can also use accelerators so that your computation can be done faster way. So like that, as one of you mentioned, Sandeep Challa mentioned, yes, definitely, instead of simply running these detection algorithms on RCNN, these then can be dumped on onto the porting onto the hardware. So hardware accelerators, we call hardware accelerators, so that everything when we are doing, so for any deep learning, we have inference and analysis, right? Training. So training, we do it on the computation, and then computation we can do using accelerators. So that is the philosophy of hardware accelerators. Training, we do pre-processing. After training, analysis or computation we do on the hardware. So there is a new philosophy is coming into picture, hardware accelerators. So if someone is interested, so we have already developed some algorithms on hardware accelerators, not on this fracture detection or on healthcare systems. We didn't do any work on this, but other algorithms we have done it. So that experience I can share with you people. You can extend that one to the whatever the real time problems on healthcare. Yes, we can work together.
Actually, there is a question from Miss Madhurika. I think this your answer now also will serve as the same for her. She's asking IoT devices keep generating a lot of data. How can we process and analyze this data quickly?
So that's about right. So if standalone IoT devices are there, if standalone CPU when it is working, this problem we are facing. But when we use this particular AI system, definitely it is going to speed up the process.
Any questions from the participants? Or otherwise, can we end the session? Yes, thank you, Professor Chandrasekhar Garu. As you have rightly said, the need of the hour in medical field is predictions based on symptoms and early detection of diseases. Added to that, easy diagnosis and treatment, where you are highlighting that AI and IoT is a best combination, where IoT ensures real-time monitoring and automation. Thank you very much for delivering such an insightful and enlightening session on IoT in healthcare. Your expertise on how artificial intelligence and Internet of Things are revolutionizing the healthcare sector have truly inspired us. From predictive diagnosis to remote patient monitoring, your
Yes,
discussion shed light on the immense potential of these technologies in improving patient care, enhancing efficiency, and shaping the future of medicine. We greatly appreciate the time and effort you took to share the knowledge with us today and the promise to work together if anybody comes up with the problem statement as well. Your engaging
yes,
presentation and real world examples have provided us with valuable insights that we will surely carry forward in our academic and professional journey. Thank you.
yes, madam.
Thank you very much,
So
Professor.
I just one message I want to give it to the young researchers, that we must see our country. Sometimes we will be seeing, so a pregnant lady was lifting for kilometers from one place to other place and all, right. So we should see that our robotic surgeries, our surgeons should go there and see that, so that such scenarios we should not see in our country. So that we have to wish. So where I submit to my all our young researchers to work towards that, so that our people who wherever are there, urban or rural, they should get ease of treatment. Thank you, madam. Thank you.
Yes, the Make in India is going on. I'm sure that the technology improvements and the young researchers will surely look into this kind of things, and surely more and more devices and facilities are going to come up. Thank you,
Yes,
sir.
madam.
Thank you.
Thank you.
Yeah.
Thank you, madam. Thank you for giving an opportunity.
Hello, participants. Ha, I think we all have enjoyed our session and have been engaged for this half an hour to 40 minutes. So, like yesterday, there was a hands-on session, and most of you appreciated it. And due to lack of time, or otherwise the heavy, like the sessions were time to time, dot to dot. So we did not find extra time to extend the hands-on. So if you are interested, before the next speaker joins, maybe we can have a hands-on session for a few time, maybe 15 to 20 minutes. In case if you are expecting or looking forward to that, you can just message in the chat box. We will arrange for the same.
Yeah, sorry. I'm audible to all of you now. Let me introduce again. Let me explain from the starting one. So we are using a DH22 digital humidity temperature sensor and ES32 to fetch data from the sensor. So for this device, we have in pin diagram, if you go to the internet or theory, we'll have 4 pins, but technically we'll have only 3 pins. One is ground pin, the other is the VCC pin, and the one more pin is the data pin. These pins are given to the ES32. One is for 3.3 volts, the other is for ground pin, one more is for any GPIO pin. Because as we are giving data digitally, we are going to read data even though temperature and humidity are analog parameters. Even though the temperature and humidity are analog parameters, this DH22 sensor converts the analog data into a digital format. Before going to use this sensor, we are using LM35, which is an analog thermal sensor. In this scenario, the microcontroller like Arduino or ESP32 has to convert data from analog to digital. Whereas this sensor has the facility which will do the things of the program control by itself. So what it will do is, it will sense the analog parameter, a temperature or humidity from the individual or from a room and convert into a digital format. Let us see how we'll read data and how to throw the data into the cloud. I'm using a Tony IDE which supports MicroPython code. Yeah, come to the code. First, we are importing from machine, we are importing the pins. Then we are importing the network to connect to the internet. Then we are importing time as we have some delay to LED on off or to fetch data from the devices. Then we are using import your request as we are throwing data to the internet. We are require U request or URL requests. Then we have a importing DHT2 library, DHT, which imports the required parameters for a temperature and humidity sensor. These are the required libraries. Then we are using a frequency of 500, and this part Wi-Fi SSID is a Wi-Fi of our environment and is a password KMIT@123. After this, we are using a DHT22. DHT.DHT22 is a built-in function to call the pin number. Any pin you can call. We are using pin number 15 here. Then, as we are creating some code here to make a condition, suppose if the temperature is more than 25 degrees. I'm visible now, all of you? Yeah. Yeah, okay. See here. We are taking one pin to read the data, and depending on the temperature, we are want to turn on a LED or turn off the LED. So we have two GPIO pins. One is pin number 15, the other pin is pin number 2. Pin number 2 is connected to any LED of the board. You can see here in the circuit or in this interface, we given to the pin number 2 of the board to have an LED. Let me show with, yeah. So these are the connections I made. You can see here. There are only 3 pins are here. The first pin is the red pin given to the ground side, and one more pin given to the 3.3 volts, and one more pin given to the data pin, and one more pin which we want to make LED on. We are taking the one more pin the board to the LED. There are only 4 connecting wires are there. One is the VCC supply pin, the other is the ground pin, the other is data pin, and the one more is, depending on the temperature, we want to turn on a LED. That's the one more pin. Let me come to the code again to explain the remaining part. Yeah, you can see here. First, we connect to the Wi-Fi network. This is the standard code to connect to the Wi-Fi. Then we come into the next one. We are using a cloud platform called Firebase. This is a standard code for connecting to any Wi-Fi network. Whether it is Arduino or ESP32, will be the standard code to connect to the Wi-Fi network. So what we are doing, we are calling the network, then we are calling the Wi-Fi name, then the password. If it is connected, we will show that connecting to the Wi-Fi network. Otherwise, it will fail. So after this, we are using a Firebase. It's a cloud platform from Google network. It's a cloud platform from Google. See here, we are defining a function called send data to the Firebase and the variable called data. We are using a method called try except. It's a famous method in the Python. If this will work, this may not work. If it is not working, you go for the exception handling. So see the code here once. The response equal to UR request. As I told you, we are sending data to the internet or to the cloud. We are using UR request dot put the Firebase URL. Whichever the Firebase I am creating, the account, there will be a URL which will be used here, and the data will be in the JSON format. As you know, JSON means JavaScript object notation. JSON means JavaScript object notation. The data will be in the format of JSON. So whatever you're getting, you will be in the format of JSON. The data will be in the JSON format. Then if this is to be pushed in the cloud, we'll see the print data sent equal to response text. So we'll get data into the text format. Then suppose this part is not executed, we'll have a failure. In such cases, you have to print fail to send data. This will happen generally if you have a problem with Wi-Fi network. This part is, first we are Firebase URL, which is we have created while creating the Firebase account. This will be the starting part, will be the URL which is given by Firebase, and you have to create a room. You have to create a room dot, you can any name there, and you can room1.json. Then that URL should be given to the code. After that, we are coming to the sensor now. Come to the sensor. While true, time.sleep, we are taking a delay of 2 milliseconds. Then sensor.measure, temp is a variable, it's a keyword to measure the temperature. Sensor.temperature. Then humidity, sensor.humidity. Then these two parameters, temperature and humidity, are sent into the cloud using send to data Firebase, which already declared initially. Then we are taking some delay of 1 millisecond. Then we are printing the humidity and temperature. And here, to show it on the cloud, we are writing a condition also. If temperature is more than 25 degrees, the light should on, the LED should on. So we are taking a prototype here. If the patient body temperature is more than 7 degrees, if the patient temperature is more than 100 degrees centigrade, the light will be on. Then we are taken delay. If again it comes down, the LED will be off. It is the code, and we'll try to run the code now. It's already we run the code already. You can check out here. We are getting data set. Humidity is 44.6 degrees. Temperature is 25.6. Right? Now I'll do one thing. This is the data generated at my end, a source side. This is the temperature in my room. This can be monitored by the any healthcare professional from a remote place using a Firebase cloud platform from Google. Let us see. I'll ask one of my friend to open his Firebase, which is provided to URL for me. She will able to monitor the data from a remote place. So I'll request Sandeep sir to make Kushi as a host, where she can able to monitor data from the remote place. And today we are giving the procedure to how to create a Firebase account also. If any, I request participants to create a Firebase account and send us the URL of their account. We'll copy that and paste it here so that they can able to monitor data from the home place. So first we'll try with our host first, then we'll create the procedure. We'll say the procedure of how to create a Firebase account and how to generate a URL. All those things will be procedure will be there. We request all the participants to create an account, share their URL, then they can able to monitor this data from the remote place. Now I'll stop sharing the screen. The other host will start sharing the screen now. Yeah, you can see here. In room 1, the humidity is 43 degrees and temperature 43% and temperature 25.4. Let us see. I'll try to rub my hand to generate some heat so that it will change here. You can check out here 25.4 is value here as well as here. You can check out once. We got same value in the source side. Now we are verifying in the cloud side or remote side. Then check out the same values are there. Yeah, I'm touching my hand now. It should increase the temperature. Yeah. You can see the LED is on because the temperature is above 25 degrees centigrade. 25 degrees centigrade. Now, in the code, we can change as per our requirement. Let us try with changing the temperature. And meanwhile, we'll share the procedure to create a Firebase. I request all the participants to create a Firebase account and please share their URL so that they are also able to monitor data remotely. We'll share the procedure in the WhatsApp group as well as in the chat so that you can create a Firebase. We are sharing the we will share the Word document to create a Firebase account. The WhatsApp which is there, please verify the procedure and practice and create an account. The WhatsApp which is there, please verify the procedure Yeah. So we shared the procedure to create a Firebase account, and if any participant have created an account, let us know. Share in WhatsApp or in a chat here. We'll keep their URL here so that they can able to monitor the remote place. How to monitor? Just now our host has shown you. So if you created an account and generated a URL address, please share to us so that they can able to monitor from remote place. And here we change the code also to made a 30 degrees centigrade so that the LED should be always off. In the previous case, it was 26 to 27. It was ranging 25 to 27. The LED was on. The next session starts by 7:30. If anybody want to have a trial, please let us know.
Good evening, all. Okay, our next speaker has already joined the session. So let me just quickly give a introduction to Mr. Naidu so that we can hear from him. Yeah. Good evening, Naidu Garu. Welcome to the session. Today, sir is going to take up a session on data management and big data analytics in IoT. As I've told you earlier in the beginning of the session itself, the first session we heard from an academician, and now it's our turn to hear from the industrialist. Mr. Guruswamy Naidu Bollineni is a seasoned technology leader with a deep passion for innovation and a distinguished career spanning computer systems, scalable infrastructure, big data, cloud operations, security, and AI. Originally from Andhra Pradesh, he earned his bachelor's degree and master's degree from Hyderabad, laying a strong academic foundation in computing. His early career at ECIL Hyderabad provided hands-on experience in computing systems and hardware infrastructure, shaping his expertise in core technology domains. Since immigrating to United States in the early 1990s, Naidu has been a resident of Silicon Valley, actively contributing to startup ventures and leading technology corporations. His focus has been on distributed systems, cloud computing, security, compliance, and evolution of AI-driven architecture. Mr. Naidu has a number of key contributions that has positively impacted industry. To name a few of them, he was among the first to integrate InfiniBand interconnect into distributed storage system, an innovation that underpins NVIDIA's scalable architectures today. He worked on ARM-based kernel programming and optimization long before it gained traction in modern AI, hardware, and edge computing. A founding R&D member of a big analytics company, helping to reinforce its strategic position in data-driven enterprise solutions. He worked as CIO and CISO, led technology and security strategies for a platform delivering billions of messages per month, ensuring high availability, compliance, and privacy-first operations. Sir has continues to push his boundaries of innovation, blending deep technical expertise with strategic leadership to drive the next generation of AI, security, and large scale distributed systems. I'm sure we are going to get immense knowledge from his direct experience with working with this kind of systems, and it will give us a new insight towards IoT in the medical field and IoT in healthcare. I welcome you, sir. We wish to hear from you now.
Okay, good evening, everyone. Hope everybody is doing good. And thanks for giving this opportunity to participate and present what my humble learnings from life and perhaps reflect and share what I know in my life experiences towards furtherment and improvement of your own learning as well as we go forward. And I want to first thank Narendra for approaching me about this particular effort. And I also thank Savita for introducing me and clearly explaining my career and perhaps personal experiences over the many decades. So if I may share my screen, and I have put together a few slides that drive us as the guidance for us to take this forward. And by the way, at the beginning of this session, I saw some Python code. I'll be happy to join and hack around if that's our goal. But this particular presentation does not have any codings, so not to worry. So speaking of about coding, I'm still little bit of a hands-on. I still hack around on Python, but at the same time, my really deep passion actually started in JNTU with Pascal and C programming. And my experience at ECL was predominantly C language. And later on, I also did a good amount of programming in assembly language and directly programming the CPUs and performance optimizations as well. And as much as technology has evolved and paradigms have, abstractions have matured a lot, you always feel your roots and how they impact your own thinking and how they actually enrich your experience and delivery of your solutions. And I actually live through these experiences when I reflect in my day-to-day work. They actually make an impact on the audience and also the co-workers who work and reflect my thinking. So feel free to ask questions anytime you have as we go forward with this presentation. And I'll be happy to have a few more questions at the end of the session as well. And so, as I said, thanks for giving this opportunity to Narendra and for KMIT to present this. So I want this session to broadly focus on two areas. One is the evolution of the storage technologies, how the traditional technologies led further to big data. And then we will detour into the healthcare, IoT, and what has been the developments there, and also what's in motion now, and what are also the challenges that we are facing in society today. And as the current and next generation students and the faculty, how you can make an impact as you go forward. I won't necessarily be able to authoritatively speak on the future, but obviously it's an opportunity for you to take that forward and be open about and question yourselves, question your peers, and see what comes and how you can improve. Okay. So focusing on storage technologies as a precursors to current generation big data systems, I really reflect again, some of these things are based on my own personal experiences. So if you really look at the hard disk as a mass storage systems, has started way back, maybe a few decades back, right? Maybe 60s and 70s. And it evolved over time. Even when there was no mass storage devices, there was actually paper tapes and 8-inch floppies, 5.25-inch floppies, and 2.5-inch quarter floppies. I know during 90s we were familiar with the 5.25-inch floppies. I started with 360 kilobyte floppy disks and 1.2 megabyte floppy disks. Now, as we saw the mass storage systems, there were two predominant protocols. SCSI was a high end, and ATA was a little bit low end. They were more or less like a parallel protocols, depending on who developed and how they matured. And as they became part of the disks and the systems that talk to these disk storage systems, they also evolved. They evolved over a period of time, and also the serial interfaces became popular. We saw like a SATA, right, which is a serial ATA, and fiber channel came to life in 90s, and also IP based SCSI also became a popular one. Now, in parallel, there were also technologies that came to life in terms of resiliency, because disks often fail, right? Physical hardware fails all the time. And for resiliency and data availability and application level guarantees, you need to have other algorithms and protocols and systems. And that's where RAID became pretty popular in 90s. So RAID 0, what we call like a JBODs, or just a bunch of disks, which is basically scaling to a higher volume sizes, and also giving resiliency using RAID 1 and RAID 5. Now, later on, more recently, you probably heard about, and most likely you're all using SSDs in your laptops and systems these days. And NVMe became a more and more popular and common these days. Again, underlying these current devices that you see are actually still based on the underpinnings of the SCSI or SATA protocols. Now, going a step above, once you understand the disks, right, then you have to have a higher level orchestration or organization of your data. And that's where you get into databases. Obviously, when we look at databases, they started somewhere around 60s, 70s, and even maturing into 90s, or relational databases. And primarily, the databases act as a medium between the underlying storage and at the top level, the applications. Now, they enforce certain disciplines for the applications to behave properly, what we call the CRUD operations: create, read, update, and delete operations, which you probably know in a typical relational databases. And they also enforce these operations for consistency and availability paradigms called acid compliance and also CAP theorem. So if you look back, what are some of the popular? I'm not going to list all the evolutions and the technologies that were there in different times, but you can name like an Oracle database, DB2 from IBM, SQL Server from Microsoft. There are also other popular commercial variations. And if you look at the open source, SQLite is at an individual device. For example, some of the small applications, when you install them, underlying those applications are actually driven by SQLite, which is a relational database, but it's more like an individual device level. You can save the SQLite on a package like a bundle and take it to another machine and save your own backups and manage those things at a little higher level. And now they became more and more popular, or MySQL and Postgres, and they're open source based. I know MySQL has been part of Oracle for quite a number of years, but that's equally popular like a pure open source Postgres. Now, beyond the relational databases, which are primarily used in the transactional operations, which is OLAP databases, primarily for historical analysis of your data, because OLTPs are real-time current moment operations. Let's say when you perform a transaction, when you do a purchase, it reflects at that moment. But how do you actually look back and correlate and see the patterns, behaviors of all the things that happened over time? This is what we call the trends analysis. By applying your statistical methods and calculations, you can derive like average, min, max, median, all sorts of values, and they tell little more on bigger stories about your own usage behaviors and patterns, and they in turn drive your actions, next set of actions, how you want to improve your own applications, systems, and also giving the user experiences go forward, so that your users have better experience as businesses compete and continue to thrive and make good on it. So if you really look at OLAP databases, which are popular, historically, you would imagine Oracle Exadata. Exadata actually came from Sun Microsystems way back. And when Sun got folded into Oracle, that became part of Oracle Exadata. Teradata is another one that used to be large warehouse systems. And later on, Astrodata was another clustered system. And Greenplum is another parallel Postgres. Now, all these systems, if you really look at underpinning, is parallel, multi-node, and highly scaled systems. Because when you're really looking at OLTP transactions, you can imagine some number of transactions at any given moment. But as you accumulate, your data grows monotonously. How do you manage that growth? That's where OLAP databases, data management paradigms come into picture. Now, there are various algorithms that are built around this, basically doing a deduplication and delta management. And once you address the storage part, then you have to do the analysis part. That means how do you access the data? How do you optimize processing it so that you still feel like you are basically reading all the data all the time and be able to derive analytics and behaviors? And so in this respect, if you look at, so we talked about the traditional big systems, and then there are more recent incarnations in this area, or like some of these are actually based out of whether it is a Postgres or MySQL underlying. There it is a CitusDB, which got folded into Microsoft. Also Yugabyte, CockroachDB. There are more of them, because you can imagine when there is a strong foundation like a MySQL and Postgres, you can imagine the gaps or perhaps personal experience and challenges that actually trigger innovations and further improvements. That's how these companies came about. That continues today. Now, when it comes to the parallel, highly scalable, distributed databases, how do you actually scale them? Right? There has to be some method. And that's where you see query analysis. That means when you fire off an SQL query, how do you actually run this query across multiple nodes? That is where you first analyze the query, and then you plan how you want to run that across the nodes. That's where the parallel execution comes into picture. Now, once you execute the query, and then you have to aggregate the results and finally drive the result to present to the end user. So that's where you can also tune based on the parallelism, and in fact, some of the SQL queries come with the additional attributes like a parallel. And you can also define some of the scalable parameters, how many parallel threads you can fire off. And some of these threads are actually defined based on the number of underlying hardware systems, whether it is number of nodes participating in your cluster, or even at a per node level, how many CPUs you have. Whether it is when we say CPU, you also know the advancements, and it came to be like a cores, number of cores, or even virtual cores in cloud systems. Now, so this is all a structured data management paradigms, right? And then came in after .com and internet explosion, came the big data foundations. The new paradigms came about, and they took a while to mature themselves. And then came the data explosion, because as the computing systems became more and more pervasive, accessible, and cheaper, and you saw the mobile devices, and whether it is a phone systems, or the other iPad and other type devices, or even IoT devices, where the data gets generated continuously. And when we talk about IoT devices, and in this context, our presentation about the healthcare, continuous patient monitoring, and other devices, IoT devices in the healthcare industry. We'll talk about that also at the later moment. Okay. So as the data explosion happened, traditional data systems, relational data systems, became a kind of a bottleneck. Either they became very costly, prohibitively costly for systems to be adopted for innovative startup companies. And that's where they actually forced rethinking and further innovation. And let's see what happens when these challenges posed innovators. So that's that led to origins of big data, right? As I mentioned, previous generation technologies. Again, if you really look at the POSIX based, did I mention the NFS and file protocols also? Because that's actually over the network, right? So NF, and so all these systems are actually forced the file protocols based on the POSIX compliance, and they were very strict, and usually they're also tested and confirmed by well-known tests. So if you don't pass these tests, usually the customers don't necessarily purchase your systems. And that means you need to have some level of rigorous building practice, product building practice, that adhere and pass these tests, so that you have a role in the business. Now, when the data growth expanded, the alternative thinking came about. And that's where the birth of big data took hold. And that started when Google presented their Google file system paper in 2003. And basically, a new paradigm where you can store large amounts of data on really, really cheap hardware, and don't have to go and buy very specialized hardware systems from highly costly vendors. And so Google basically what they did is they took typical workstations, because see, workstation prices, because they are built with lower end uh, hardware components, and thereby being cheaper. But at the same time, Google adopted them in such a way that you can actually deploy them on many, many nodes, where the actual resiliency is built by a higher level abstraction and not necessarily underlying device and the hardware itself. So after Google GFS got presented, that also led, whether it's directly or indirectly, because other peers were always looking at the innovations going on. So Yahoo came to define their own Hadoop, right? So the Doug Cutting and his colleagues started making an open source version of a system that is similar to Google's file system, where basically you store the large amounts of data on a distributed, pretty much independent systems. That means any system can fail at any moment, and your the on the next level Hadoop or whatever file system, what we call, can actually address the failures. So while the Hadoop was actually taking hold during early 2000s, there were also some parallel technologies that enabled and became part of the next generation of overall systems. That's a the search that came from Google, because while the search was there even in late 90s and during .com, that became more and more popular, and also open source versions based on the Lucene, whether it is a Solar or Elasticsearch, two different variations are based on the Lucene, and they became popular. So combined with Hadoop and the text search, the new products started coming out. Now, as I mentioned, GFS storage as a solution, right? So basically storing on a cheap hardware by doing a three-way replication, distributed, and data redundancy. And so node replacement became an easy thing, because the data resiliency and somewhat self-healing mechanism is built into this system, whether it is a Google file system or Hadoop. So when that happened, when you store the data, you still have to process, right? So as part of Hadoop came this map reduce the logic or algorithms and these libraries. So how do you access the data? How do you give the confidence that the data is still sane, or its integrity is maintained, so that when your application consumes the data, it is valid and it is not corrupt or it is not stale, right? So this is where the MapReduce algorithms came about, and they actually, the other shift here that you imagine is, see, we saw the POSIX based, the strict protocol based file systems before, right? Now the Hadoop and Google file system became little more free in terms of thinking, and became like a unstructured data processing, less stringent about accuracy constraints. And so that actually enabled all this other social applications also, because now we are talking about loosely coupled data that is continuously coming, and so you process as the data comes in, because also what happens is the data relevance is lost if you lose time. Let's say the the data has to reflect what's happening now, so that you can tune your behaviors quickly, because what happened 6 months back may not be so relevant today. So and in this scenario, the other thing also became is the caches, right? So if you really look back, system had their own processor level caches, whether you call it as L2, L3 level caches, on chip cache, and all those things. But the big systems and big data systems actually brought the whole concept of cache in between, which is basically because the latencies from these Hadoop systems were much higher. And that means you need to have a little more an intermediate level. That's where the Redis and even storage driven Kafka, all these things became popular. And they enabled web scale data processing and enabling the next generation of social applications. Now, as we saw in the early 2000s and mid 2000s, these technologies were getting mature. Over time, as their adoption and the social applications became more and more popular, there are more companies that came to build these Hadoop and open source based systems. The popular ones I listed: Cloudera, Hortonworks, Mapper, and Pivotal. They're all based on Hadoop paradigm, and they actually pretty much adopted open source Hadoop, except for Mapper. Mapper actually tried to re-implement Hadoop in their own version of C++, because see, Hadoop was actually implemented with Java as the core language. So Mapper tried to do it differently by doing in underlying C language so that your JVM overheads are removed. But again, that became their own headache also, because now you have to deal with your own compliance and a common thing, interoperability challenges. Now, so as much as these companies came to life and were getting matured, there were also some underlying challenges with Hadoop, because this challenge, because it's again, so we're talking about loosely coupled unstructured data management, because there are no strict policies and protocols like a POSIX that imposes restrictions. When we say restrictions, that also gives you the simplicity. When you remove the restriction, it actually becomes your flexibility that adds a lot more complexity. There's kind of a mutually contending arguments there, right? So the complexity actually brought a lot of open source tools during that time. There were a number of tools on top of Hadoop, what we call like a HBase and Hive. And there are also other associated tools for a cluster management, file management, and also the data access, whether it is a, call it as SQL type operations, like from HBase and Hive. So all these things became a ton of Apache based tools and services. Now, so this whole thing is actually around Hadoop as a kind of a core, the foundation, right? Now, in around 2010, maybe before or after, there are also other variations of non-SQL or non-relational databases that came about. So one distinction that I wanted to make here is, if you remember earlier, I mentioned about the CRUD. The NoSQLs started calling themselves as crap, because it's not really crap here, but what you say is create, read, append, and purge. That means when the systems and the data is exploding, how do you actually manage? Update doesn't really make sense, because the older data is losing its relevance very, very fast. And that's why you keep appending the data, and the older data you can probably purge. So now, of course, you can still apply the CAP theorem, because you still have to manage distributed storage systems, and you need to have some amount of guarantees, consistency, availability, and partitioning challenges. And so a couple of the NoSQL databases that came about, one was from Facebook called Cassandra. Cassandra itself has its own SQL similar to SQL, and it has eventual consistency, three-way replication, and self-healing mechanisms built in. Now, when Cassandra was actually became part of open source, there are other companies that came to life based on this one. Just like the first set of Hadoop-based systems, next set of systems came, and businesses, DataStax, ScyllaDB, and even the hyperscalers like Amazon adopted that as a DynamoDB, Azure, the Google, these guys. So they pretty much give you SQL type interfaces, and you can run some queries. They don't necessarily adhere and give you all the capabilities of traditional relational SQL capabilities, but they largely enable you to process your unstructured data. Now, in this context, there are also a couple of other variations. MongoDB, it primarily prides itself as a documented database, and it became popular where you can save the whole document and not necessarily as a structure with it, right? And then also Graph Database by Neo4j. That means as the data is exploding, how do you actually connect the data and get the relations? You really apply the graph theory, and you can actually take that and identify the patterns out of that. Okay, so out of this one, now the next set of maturity and technologies came about, right? As we talked about the limitations of Hadoop, those were addressed by Spark. Apache Spark is after 2010, right? So this improves upon Hadoop's core principles by doing a delta processing, and you don't necessarily have to fetch all the data every time going to the system and processing it. So what they call like a Spark has RDD, resilient distributed data set, and that means you build intermediate results, and you use the results and you iteratively speed up your processing. So that means you don't really see every time you have to do some processing. Let's say, for example, a scheduled job, right? If the data does not change, or your change is only maybe like a 5% or 10%, you don't go and churn your 100% of the data, which Hadoop was doing previously. So Spark became very, very popular, highly efficient performance system. And this also became part of modern machine learning algorithms, and that got adopted into, and some of the Python based libraries also came to life during this time. Now, based on this Spark and advancements, there are new companies that came to become like a modern warehouses, whether it's a Snowflake, Databricks, and they're also combined with the data storage systems on the major public clouds. Think about whether it is a AWS, uh, S3, or Google Cloud Storage, or Azure block storage systems. So you can store immense amount of data and apply these open source technologies and do the faster processing, derive the analytics. And even these companies which are offering analytics, whether it is Snowflake and Databricks, they have the integrations with these underlying storage technologies. And then you also combine with the rise of streaming technologies, because see, as much as you are doing uh, data processing, as the data is continuously growing, your problem is not being removed. So you still need some amount of data caching. That's where the Kafka or Apache Flink became more real-time data ingestion and processing. There are also other variation of a Kafka called Stream Native, another company that does that. So if you really look at why Kafka and this became famous, is because when you are flooding your data into your system may not have the ability to absorb all that and store in real time. That's where Kafka became like your cushion, so that it will grasp the data as it is coming, and you have the ability to offline processing it at your own leisure time. So that it's basically like an intermediate lake for your river stream, right? So you can tap that into that intermediate lake and then process and store it into your final resting place. Now, also these systems turned the whole warehouse paradigms, the traditionally what we used to call ETL processing, right? Extract, transform, and load became like ELT. That means extract, load and then transform. Because see, some of the systems have also become cheaper. You can just load the data and not worry upfront, and then you can transform. And it also became more and more paradigm in the cloud environments. Now, another aspect to this whole thing is the languages, right? So, because the data paradigms and old languages may not necessarily have the constructs, or maybe more difficult building those things, the functional languages became pretty popular during these times in the last 15, 20 years or so. So they give you speed of your own application development, and they enable your memory protection, some of the issues that traditional languages like C, C++ had, without having the overhead of JVMs from Java. And combined, they give you higher performance. And recent languages that I could speak is Scala, Clojure, Elixir, Rust, and Haskell. And you should certainly look at these languages and see if it makes sense. And there may be some specific applications for specific languages. It depends on what you want to do, and you can read more about it. And if I have to look back, we also had these functional languages during our days in 80s and 90s. I know in our college we used to do a Lisp programming, and my final year project was on Prolog. It happened to be on a healthcare expert systems, and even our classmates were actually writing the interprets for Lisp. So yeah, we are not totally removed from that, but it's the new languages that came about. So okay, I think I covered a good chunk on the actual storage systems evolution, where we came about and what the current trends are like, right? So you can definitely read about Snowflakes and Databricks and Apache Spark and machine learning algorithms as the keywords, and adopting some of these languages. Now, shifting gears a little bit into what's happened historically on the healthcare, right? So over the last 20, 25 years or so, a lot of the protocols and remote sensor technologies have been developed. They've been developed using different communication protocols, whether it is a Bluetooth or a Zigbee or a Wi-Fi or internet capable, right? And so when we say remote sensor technologies, all these sensors are really, really very low powered and very small footprint devices that have to be, they should be fitting in your pocket. And they don't necessarily produce like a very large volumes of data. But when you actually combine and deploy them into hundreds and thousands of millions of devices or large populations, large areas, they still produce huge amounts of data. And that in turn becomes your big data problem. Because again, when you're looking at, think about, for example, sensors producing your weather data, right? Your weather data is very, very important and critical to reflect and give forecast for the next 24 hours based on the last 24 hours or last 1 week, but not much of an immediate use if you're really looking back at 6 months, right? This is where the crap for a big data becomes relevant, right? So you are basically opening more and more data, and you are at liberty to purge very old data, unless you really want to have a very long term uh, trends, in which case you don't really have to have all the data. That's where your aggregations come into picture. You roll up and you keep, like, instead of doing every minute, you can say hourly or a daily. That's good enough for you to look back and say 6 months back what happened, but you are not going to look at that particular minute what happened 6 months back, right? So that's where the roll-ups come into picture when it comes to the analytics process. Now, when the remote sensor technologies became more and more available, the wearables started coming into picture. So personalized health indicator measurement devices owned by individuals, and they give specific data on demand, hourly or daily, and indicate health status of individuals wearing them. And over time, this data forms patterns and trends for review by either the device owner on his or her own personal device, like mobile apps, or even professionals using that data and doing some recommendations and guidance for behavior changes, or even businesses aggregating this data and seeing bigger trends and doing their own product improvements, or maybe selling this data at an aggregate level to professionals who can utilize data and offer their own recommendations to their end users. Now, of course, then also came mobile applications, and it became much easier for individuals to wear these devices anywhere, anytime, and even further improvements like a Apple Watch, accident detection, and emergency dialing. And so, when you are producing this amount of data, you're deriving intelligence from this data, right? Again, as I said, millions of devices constantly streaming data, and running analytics and finding patterns and trends is still a big data problem. And while all this being done, we can never ignore preserving the privacy and offering safety of the individual who is producing the data. Imagine if you can relate to one particular data behavior that speaks about an individual. Now that individual may be at risk for whatever reason, right? The individual may be mocked by their his or her peers and make fun of individual and humiliation, or maybe data and other theft that may entail. All these things come into picture. So healthcare systems and health data privacy and regulations have become very, very critical, and they also came into life over time. Now, if you really look at the areas of impact and interest in healthcare, right? See, the healthcare market has become so big because, see, that's probably for any nation, that's the single biggest industry, perhaps after or maybe even before your security and military, right? In US, the current trends are like close to $5 trillion, and India annual spends happen to be around tenth of that, which is 400 billion or so. And so in the healthcare market, the other aspect is patents are pretty much strictly enforced. And as they expire after 20 years or so, generics also come to life, and they offer cheaper alternatives to those patented medicines. Now, if you really look at the whole healthcare and IoT and big data combined, there are large number of sub segments within this whole big domain, right? Personal care, individual care is one specific area, right? We'll look at more details in the next couple of slides. Remote patient monitoring and wearable IoT devices. And when it comes to the systems, analytics, computing systems, predictive analytics, AI, and all the algorithms, and obviously Python became pretty popular. And there are a number of machine learning algorithms and libraries, open source libraries that one can consume and readily process the data. And even the data sets are available for you to be able to play around and understand and learn about these things, so that you can actually apply when there is a need for a similar problem. Now, you can also think of IoT and big data problems solutions applied in the smart hospitals and IoT based medical infrastructure, right? Hospitals and healthcare providers, whether it is doctors and small shops, right? They all use these devices. They're also IoT based, and they enable speeding up their delivery of the service. and also better management. Now, you can imagine during COVID, we all benefited with the telehealth and virtual care systems. How was that possible? Because some of these IoT systems actually have enabled individuals wear and measure some data and be able to share it securely with their doctors and the hospital systems. And when you look at other area is genomics and personalized medicine, right? When we say genomics, the whole human genome sequencing that was done. If you really have to imagine, think of all the combinations, right? The chromosomes and the combinations that can happen, and there is no way that you can fit all the data into a relational databases and be able to query and generate the intelligent. This is where the big data systems really enabled in a really significant fashion. Now, when you apply these algorithms and genome sequencing, you can actually come to really a personalized medicine. That means you can tune the medicine to at an individual level. And so during COVID, we also know about the real-time epidemic and disease surveillance, and we're able to communicate. And so applying IoT and big data systems to drug discovery and clinical trials, and mental health monitoring with IoT and AI. And there are also blockchain and data security in healthcare IoT, right? The further improvements are 5G, edge computing, and IoT in healthcare. And we also talked about information security, patient data protection, privacy laws. Now, I wanted to categorize the previous slide a little more differently to see where we are in terms of big buckets. These may not necessarily reflect the exhaustive list of things, but give you a kind of a high level, right? Whether it is a personal health, fitness devices, tracking the vitals, smart medicine dispensers, because based on the vitals that you gather, you can actually define the actions on, and even the baby monitors. And we'll see more in the next couple of slides on the personal health. And on the hospitals and care providers, remote patient monitoring, and hospital smart asset tracking, and virtual care visits, and remote surgeries. Also, remote surgeries has become a pretty common thing these days. So you have the robots, and you can really continuously monitor and do some of the surgeries even remotely. And when it comes to the drug industry and equipment builders, again, they benefit significantly with the massive data and better and faster analytics. And they also have their own challenges with asset and inventory tracking that they are able to do better. And faster drug recovery, because the big data systems enable a lot of these analytics and analysis, and combined with the expanded genomics. Now you can imagine the governments and non-governmental organizations. For example, you can imagine John Hopkins became popular with their COVID tracking during COVID. And vaccines discovery as well as distribution. We can all imagine, we have lived through COVID, and it's fresh in our memory how quickly governments are able to help discover the vaccines and able to disseminate and protect individuals. And so you can also imagine the big data systems enable the tracking the trends and disaster management, right? Now, the other aspect is fraud prevention and compliances. So this is an ongoing challenge and we can't ignore. And so that's where governments impose and define the policies for the protections of the individuals and systems as well. Okay. Now, if we dig a little more into personal health area with IoTs, imagine what are the goals of all these applications, right? At the end of the day, when you talk about health, reducing the hurting or the pain of an individual at the most minimum, right? Or proper physical and mental function. You can even think about measure, algorithmically decide, and act autonomously. This is actually something that applies when it comes to like your continuous glucose monitoring or heartbeat monitoring, all those systems. You can measure the actual vitals, and your algorithms can be coded into those devices to act. For example, when your glucose falls below certain levels, the devices can actually induce some medicine autonomously, right? And so at the end of the day, individuals want their self-sufficiency, less dependency on others for their own personal movement, even whether it is dignity or for cost factors. Now, if you look at a higher level, people want to live longer, and death being the ultimate fear. And you can imagine IoTs and healthcare improvements over time has actually improved the life expectancy. Now, if you really apply all these things, you want this to be personalized. Everybody is unique, while patterns appear over the larger population. Now, another aspect is the cost management, right? How do you purchase these things? You can go directly purchase them without any prescriptions, or certain devices and maybe require some prescriptions as well. You may have insurance that pays for it, or maybe government or NGOs may assist purchasing these things. Now, there are some devices and practices that require subscription models. For example, continuous glucose monitoring and dispensing devices, they need some refills. If you need the refills, you can actually subscribe so that they can send you, and they do cost some. Right? Again, they may be covered by insurance, or you may be able to purchase yourself. Again, compliance applies here, and regulatory upload of devices, because you don't want the duplicates and the fake devices that are scam you, right? And because the regulations are in place, they also take longer for reviews and approvals. Now, but again, at the end of the day, as your sales scale, you will be able to offer them at your more reasonable prices. Also, competition and innovations drive the prices down. Again, think about data handling and privacy, internal access controls, right? So when you have the data, there's big data coming based on a particular individual's own measurement equipment or mobile devices. Now, how do you use that data inside the company, right? For a testing purpose or a validation, and for improvements purposes. And for external sharing, say if you have the data and you want to share with your service providers or doctors, and for a cost management, for example, insurance may want to see your data. How do you share the data securely, right? Now, how do you actually protect from unwanted access and hacks? These are the challenges on an ongoing basis. Now, if you really look further down, deeper into wearables and IoTs in personal health area, there are a number of them that you can list them, right? So you can imagine these things have been so advanced in the last couple of decades, and continuous glucose monitoring has been one of the really great success. Fitness monitors have become pretty good. Hearing aids have been there. Even the vision equipment like augmented reality, virtual reality devices are coming there. And your heart monitoring, ECG monitors and pacemakers, and at home dialysis equipments for kidney malfunction patients. Then there are also cosmetic, the healthcare services, whether it's a dental products or even beauty related ones, and Weight Watchers has become another big thing. You remember, like old days, we only had access to our weighing machines on the railway station, right? There are bone implants and even sleep aids have become more common these days. And exercise equipments are there. You can imagine the watches like Apple Watch, not only health monitoring, fall detection, and emergency SOS dialing facilities these days. With all these things, now you have everything at your fingertips with the mobile application assistance. And the mobile applications, again, the application providers can aggregate the data and see the patterns and even take advantage of those things. Now, you probably heard about Neuralink from Elon Musk's companies, which is now doing research on the brain computer interface and altering, and perhaps the goal being improving uh, interactions and cognizance. Now, there are also other pain altering at the source. This is another thing that recently came about. You know, the pain is always is ultimate indicator from the brain nervous system. Now, what if you can actually alter pain at the source? Let's say if your wrist is paining, it doesn't have to be acted on by the brain nervous system. Is there something that you can actually do at your wrist level? These are similar to like your edge computing, right? You don't have to have everything done by the central system. Now, of course, you can also imagine the satellites network connections becoming more and more ubiquitous, and they enable tracing and even last person tracking. Now, think about all these things applying to alternative medicine, right? So, Eastern societies like India or China or other areas, right? There are not a lot of alternative medical practices. Now, IoT is enabling even in those areas, right? Now, perhaps one of the simple ones that you can think of is modern community groups and using the application, mobile applications for meetups and walk groups, and IoT and smart yoga mats and Tai Chi motion tracking. And of course, at the end of the day, we can't ignore the challenges. Unregulated, so that means people must be educated, not for the falling for the fake offers. Now, let's combine these things. So if you remember the first 4 slides or so, we talked about the big data evolution. In the next 3 or 4 slides, we covered the whole healthcare domain. Now, combined, what are the things that have happened, right? So in the original structured data digitization happened in the late 90s, where electronic health records and EMR systems became popular. And that's more of a digital transformation, but still rooted in the structured data systems. Adoption of Hadoop in government and research institutions then opened up a lot more and bigger opportunities and advancements. And large health data systems are available, mostly anonymized. I don't think anything is uniquely identifiable. And these data systems are also shared for research so that there is a greater good that comes out. And these enable new medical discoveries and technology innovations. Now, how do they help? By allowing predicting the trends, planning, and reactions, right? Data-driven predictions and information dissemination. Think about like a pandemics or epidemics that happen across globe in various regions. How do you actually tell different others so that they can actually do their own actions and taking the reactive steps? So we talked about genomic sequencing and how the personalized medicine can be designed and offered, right? Now, all these are possible because now you are also talking about cloud-based healthcare initiatives, because cloud systems and data hosting has become pretty reasonable and cheap and affordable for large wide area of businesses. And so the data sharing and that inspire a lot of innovations. And even the cloud systems companies like Amazon or Google or Azure, they offer some credits for encouraging small innovators to actually start doing and not be left back, so that the ideas come to fruition. Now, when it comes to the libraries, open source projects, they're available: Pandas, PyTorch, TensorFlow. You probably heard about it, and good to start playing with them, learn about them, and see how they can be applied to areas that you see the need for. Okay. Now, I would say this is probably my last slide. So I want to talk about what's more to be done, right? We didn't really cover too much about the blockchain, but blockchain has been there, crypto, and that really gives you ability for immutable storage that protects data from hacking, and also gives you decentralized storage, so that any single copy losing is not an immediate problem, and gives you overall security and personal privacy. Now, we are living in the AI world, where the cheaper and faster hardware with more popular language models becoming accessible, you'll be able to probably build digital twins. And of course, there are companies who are also building humanoids that drive care management as well. Now, all these things enable enhanced clinical trials and faster drug discovery, and even personalized medicine, and further improvements in the healthcare domain. Now, in terms of the communication technologies, as I mentioned, satellite connectivity, 5G, and edge computing really enable innovative thinking and innovative solutions, so that you don't necessarily have to have all the data pumped to the central system and processing all in one place. You can do that at the edge, have a edge more specific localized offerings, and while you can still push your data back to the central system eventually. Okay. Now, we didn't mention about the drones, but drones have become pretty much ubiquitous again. They are there everywhere, and you can imagine applying the drones for surgical and urgent health needs, right? You can transport critical equipment or supplies if there is a need for between the systems that are sharing, right? And delivering the medicine to chronic patients on a regular basis, and reducing the office visits or hospital visits by doing these things is possible with the drones. Now, policy sharing for better benefits, intergovernmental collaborations, and having common standards and tools and practices definitely help. And so some of these global public data sets, which are accessible openly, will help in doing better processing and better understanding. And and of course, these are enabled with a high-speed connectivity and super fast hardware at affordable prices. Now, there are also new challenges the current generation and the next generation of populations have to face, right? Human-induced pollutions, whether it is a forever plastics or other pollutions that happen, and natural disasters are an ongoing thing. So these are the things that come to mind, and I think this is probably my last slide. Okay, so I'll take a pause, and I'm happy to take questions and answer anything.
Hello, everyone. Any questions? Anybody? Well, in that case, shall we wind up? Anybody on the chat box? I'm just checking for it, sir.
Okay, Thank you very much. Thank you, Savita and Narendra, for giving this opportunity for all the audience being patient. And I'm happy to take up any questions offline. And Narendra is my immediate contact.
Yeah,
And
yeah. Sure, sir.
thank you,
Sure.
ma'am.
Just, yeah, yeah. Yeah, thank you very much, sir. Thank you for delivering such an enlightening session on the role of big data in IoT and healthcare, especially the insights on evolution of storage and data organization provided us with a deep understanding of the technological growth as well. Your discussion on how big data combined with IoT is transforming healthcare has provided with valuable insights into future medical innovations. The way you highlighted the IoT supported wearables from the most common smartwatches monitoring vital signs to the real-time patient tracking devices or the Neuralink for brain functionalities, especially demonstrated the immense potential of technology in improving patient care, early disease detection, and personalized medicines. So we truly appreciate the time and effort you dedicated to sharing your expertise with us, sir. Your knowledge and the real world examples have not only deepened our understanding, but have also inspired us to explore possibilities of data driven and connected healthcare. So, on behalf of KMIT and all the participants, I sincerely thank you once again for your invaluable contributions. We hope that we have the privilege of learning from you again in future. As you have said, Narendra sir is your immediate contact. We will keep troubling you maybe through him. So, waiting
Absolutely.
for the
Absolutely.
opportunity. Sure, sure.
I'm
Thank you.
happy
Thank
to
you.
share whatever I learn and happy to reflect as the opportunity is presented.
Yeah.
It's a good opportunity as well. Thank you.
Yeah, thank you so much, sir. Thank you. Thank you. Participants, the feedback links have been provided in the chat. Please do fill the feedback forms before exiting from the session. Thank you.